When we talk about the properties that something has, especially in mathematics, what we're really looking at on an informal level is what can we get away with in that space. So for example, we know that vectors have something called scalar multiplication. So I'll say we have scalar multiplication. Which means that for any k that is a real number, that is saying that k is an element of or a member of the set of things we call real numbers. So k is a real number. If k is a real number, then I can do this, k times any vector v, where we have previously defined now what a vector is, or a vector in a vector space is a collection in a particular order of real numbers. So for example, if I have v equals 3, 0, 1, then 5v equals 5 times 3, 0, 1, which is just the vector 15, 0, 5. I can do that in the Euclidean vector space. I'm going to introduce another cheeky little symbol here. I'm not going to require that you use this, but I know some of you are really kind of interested in all the little ins and outs of things, and so I'm just going to introduce it so you'll be able at some point to say that you've seen it and you know what it means. If I write the upside down capital letter A, I mean for all of the things that look like this in this set. So for all numbers k that are real numbers, so for all real numbers, this multiple of a vector means this. This is just an example down here, but that's what scalar multiplication is. For all, you could say for each, or for every, or even for any k that is a real number, scalar multiplication exists. That's a property in the vector spaces. We already know that one, but it is a property in the space of vector spaces as well. So I thought I'd mention that. And the other one is scalar addition. Here I might write for all vectors u and v in the set of things we call the vector space V. See now why the capital is so important? U plus V is defined. For every U and V in the vector space V, the addition of two vectors is defined. I've added the scalar multiplication is defined as well, and I've cordoned this off so that we don't get confused. Now, there are some important specific vectors that we need to make sure we know about. And again, we've already discussed these, but we'll do them again. We have something called the identity. And the identity is just the thing that you operate on a vector by, or a real number. In this case, it's a vector, and that returns the same thing. So in the real numbers, for example, if I have the number a, the additive identity is 0 because I get the same number back if I add 0 to a. The multiplicative identity is 1 because when I multiply a by 1, I get a back. In vector spaces, in a vector space, the additive identity, well, remember that you can only add a vector to another vector, so that vector must be all zeros. We can write that as a 0 with a vector symbol over it, or you might see it as a bold 0 in type, or even italicized. Lots of different ways you might see it. In writing, in handwritten work, it tends to have a vector bar over it, half arrow. That's the additive identity, because if I add that vector to any other vector of the same dimension, the result of that addition is my original vector. It doesn't change. It doesn't give me a new vector. It gives me my old vector back. The scalar identity, that's a little tricky because remember that a scalar is just a single number that we multiply through. It's kind of like distributing through. the vector, and that scalar, in order to return the original vector, that scalar has to be 1. So we have these two properties of scalar multiplication and scalar addition, and these two special vectors that help us work with vectors in a vector space. Something that we haven't talked about yet is inverses. The additive inverse of a vector u, let's see, I think I'll just try to do something of an example here. Let's do it with real numbers. 2, 1, 0 plus, remember that the inverse, either additive or multiplicative inverse, in real numbers, the additive inverse of A is the thing you add to A to get 0 back, to get the additive identity. And that's going to be negative A. The multiplicative identity of A is the thing that you add to A, sorry, that you multiply by A to get the multiplicative identity. And that's going to be 1 over A. Well, for vectors, the additive identity is the thing, another vector, that you add to your first vector to get back your additive identity. So the additive identity here is going to be negative 2, negative 1, 0. Because component by component, when I add these together, I get 0. I get the 0 vector. What would the inverse scalar multiple have to be? Well, by way of argument, a scalar inverse multiple would be the number that you multiplied by your original vector. I'll use the same one here, 2, 1, 0. So that when you did that multiplication, you got the multiplicative inverse. Well, first of all, a scalar has to be a number. Let's call that number p. What the heck? But this is not a vector p, it's just a number p. What number do I multiply by this vector to get a number out? Well, I don't. When I multiply this number by this vector, the result is going to be a vector, not a number. So there is no such thing as the scalar multiplicative inverse. But the additive identity of any vector, I've used horizontal notation here just because of the space constraints. The additive identity of a vector is the vector made up of the additive identities of the components. Well, most of what we've just talked about is stuff we really already knew about vectors. The additive inverse is a little bit new, but it's not a hard thing to tack on to what we've already experienced. Something we're going to talk about now, though, is a little bit different, and I'm going to take another step back and remind you about something you know from arithmetic, mostly by just having done it a lot. If I take a number A and I add it to another number B, let's start by the fact that A and B are both real numbers. It's always going to be a number C where C is also a real number. So what we say about this is that real numbers, let me do it this way, the real numbers, that set, that collection of things we call real numbers, everything in there, that set is called closed under addition. And all that means is that if you do something, this addition thing, if you do that to two of the things in this set, you get another of the things in that set out. Here's an example of one that's not. Let's do A minus B equals D. Notice that these two things are the same, right? If I take A and B in R, put that over here. A and B are in R. When I add them together, I get C, which is also in R. These two things are the same, and we say then that R, the set, is closed under the operation that we did. I'm going to start this one over. I'm going to say that A and B are in the set Z plus, and what that means is positive integers. Okay, then I can say that A minus B equals D, but D is not necessarily going to be a positive integer. I can give you a counterexample. If A is 1 and B is 3, then A is a positive integer and B is a positive integer, right? They're both in the set positive integers, but they equal -2. When you subtract them, you get -2, and -2 is not in the positive integers. So we say here that the set Z plus is not closed under the operation that we tried to do it on it, which was subtraction. What we're working with here is a property of something called a field. And it turns out that the vectors are a field, which is why I'm getting into all of this. We're not really going to be working with fields in general, but these are properties of the field we're going to call the vector space. Okay, let's look at multiplication. For the same A and B in the set of real numbers, A times B is equal to, let's go K. I'm trying to use different numbers here because A plus B is equal to C. So A times B is not likely also to be equal to C. Well, if we do that, if A and B are in real numbers, and we multiply them together, we get another real number, K. It's another, A and B are real numbers, and when we multiply them together, we get another real number. So we say the real numbers are also closed under multiplication. The set of real numbers is closed under multiplication. It turns out that the real numbers are also closed under subtraction. If I changed these Z pluses to R's, then I would say that the real numbers are closed, right? The set of real numbers is closed under subtraction because when I take a real number, and subtract from it another real number, I'll get a number D, which is also a real number. Okay, so the real numbers are closed under addition and subtraction, multiplication and division, because when you divide two real numbers, you get another real number. So the real numbers are a pretty robust set of numbers. They're closed under many operations. Those are the four primary ones, of course, but the real numbers are also closed under the operation of square root, under the operation of cube, under the operation of exponentiate. But that's the real numbers. As we've seen here, not every set is closed under every operation. There are some sets that are not closed under every operation. What we're going to do now, though, is we're going to look at the vector space and see what that set, how that set is closed, or where that set is closed. And then we'll also go on to look at some of the other properties of vector spaces, but most of those you will already know. Okay, so what I was playing around with before on the previous screen was the real numbers, the set of real numbers. Now what I'm going to be playing around with is the set of vectors, and in particular, the set of vectors in V sub n. And what I mean by that is that, for example, in R3, the vector space R3, the properties we're about to discuss will hold, but they will also then hold in R4 or R17. So I'm talking about vector spaces in Rn because what I'm about to say is true for any given n value. So although I have to operate on two vectors in R3, if I'm in R3, I can't add together a vector in R3 and say R5. As long as the vectors are in the same space, these properties hold. And here's what we have. We're going to start by defining the vector space as the collection of all vectors. Notice that I've listed 3 here, but this list goes on forever because there are an infinite number of vectors in this space. these vectors are defined, so the vector space is defined by these vectors, and these vectors are in turn defined by being in Rn. So whatever n is, it has to be the same for all of these vectors, all the ones listed and all the ones not listed. I've also listed a couple of numbers here that are in the real numbers. These are going to turn out to be scalars. We need to have a couple of numbers defined as just being real numbers, and we know that that's what scalars are. So as we use these as scalars, we'll know we can get away with it. There are 10 properties of vector spaces we need to discuss here, and I'm not sure I'll get them all on the same screen, but I'm certainly going to try. Let's put that up here. The first one is that vector spaces are closed under vector addition. If they're closed, they have closure. And so what that means is that if I take any two of my vectors, I could use u and v or u and w, or doesn't really matter. If I add them together, the resulting vector is also, just like u and v are, that resulting vector is also going to be in Rn, right? Remember we said if we add two real numbers together, we get another number that is also in the set of real numbers. Here what I'm saying is if I add two vectors together that come from Rn, then the result of that addition is also going to be a vector in Rn. And that's what we mean by when we say that the operation is, that the space Rn is closed under the operation of addition. The set of vectors in Rn is also closed under scalar multiplication, because if I take any number a and I multiply it by any vector, let's use u, I'm trying to be consistent with your textbook here, that multiplication is going to produce another vector that is in the same subspace. It's still in Rn. By multiplying an n-dimensional vector by some constant, I'm returning another n-dimensional vector. This symbol again just means is an element of, it's a funny little e. I like to think of it as being a member of this collection, this operation that I've done here. Take a and multiply it through a vector u. The result I get here is an element of, or is a member of the set Rn. Okay, those were the two properties we get from fields, but there are plenty of others, of course. The commutativity of addition just means that if I take u and I add it to v, I'll get the same thing as if I take v and add it to u. These two things are equal. And that's a property that we're already familiar with. It looked a little bit different when we were doing things with matrices. If I take two similarly sized matrices, identically sized matrices, and add them together, the result is the same, regardless of the way I do that addition. Vectors are just specialized matrices, right? They're either column matrices or row matrices. So we have commutative addition. We also have the associativity of addition. What that says is that I can associate two vectors by addition in one version of my work in the problem, and I can associate a different two in a different version. So u plus v plus w and u plus v plus w will have the same result whether I first add together the v and the w or whether I first add together the u and the v. Those two will be the same. That's the associativity of addition. The additive identity is a unique vector in Rn. You might see it annotated this way, the nth dimensional zero vector. And what the additive identity says is that for any vector, I can pick u, v, w, or anything else in that set. When I add 0 to it, I just get u back. Because of the because of the commutativity of addition, I can take u plus 0 or 0 plus u, and I still get u back, right? So whether this says u plus 0 or 0 plus u, I'm going to get u back. When I showed you the additive inverse on, oh gosh, I think that was 2 or 3 screens ago, it might have even been in a previous video. I said that if you had a vector, I'm going to write this and then I'm going to erase it because it's going to take up too much space. Let's say you have a vector x1, x2, up to xn, and you added that to another vector. If the result was the 0 vector, the additive identity, then in order to get that, because of the way we add matrices or vectors together, this component here is going to have to, when I add x1 to this component here, I'm going to have to get 0. And so that's negative x1. And I'll do the same thing for x2 and xn, right? Another way to write this, though, this vector here, is negative the vector x1, x2, xn, right? It's kind of a scaling. Well, if this is vector u, and I add then the scaled of the same vector, right? These components here, x1 through xn, that's just vector u. Then I can write this as u plus the opposite of u equals the 0 vector. Okay, so now let me erase this work that I've shown down here to show you why that's the case. This notation's a lot more compact. U plus the opposite of u is the additive identity. The associativity of a scalar multiplication we've talked about before as well. If I take a scalar A and a scalar B and a vector u, let's write that out twice, then what this associativity of a scalar multiplication says is that it doesn't matter whether I scale my vector u by b first and then multiply that or scale this resulting vector by a, or whether I just multiply my real number scalars together first and then multiply that or scale u by that result. It doesn't matter which I do, I get the same result. That's the associativity of scalar multiplication. We talked about this one at the same time. If you multiply any vector by 1, you get the same vector back. So 1 is what we call the scalar multiplication identity. Remember, we also had identity matrices that were all 1s on the diagonal and 0s everywhere else. That's a little different. So that's not what we're talking about here. We're specifically talking about the scalar multiplication identity, and that's always 1. The distributivity of scalars under addition just says that if you take, let me rewrite that a little bit. The result will be the same, but let's do it this way first. If you take two vectors and add them together, and then the result of that will be a vector, right? U plus v is a new vector. That will be a new vector. If I scale that vector by a, or if instead I choose to scale vector u by a and vector v by a, and then add those two together, au will be a vector, av will be a vector, I'll get the same thing. This is the distributivity of scalars under addition. Okay, that's the one I got when I added the two vectors together first and then scaled them. I'm using the same scalar here on the two vectors independently, or I'm adding the vectors and then applying the scalar. But if instead what I do is add together two scalars, let's see what happens then. If I take the scalars a and b and add them together, and those are both real numbers, remember, they're just numbers, and I multiply the vector u by that new number, then I'll get the same thing as if I had scaled u by a and scaled u by b and then added them together. So I've reversed the words here, the distributivity of scalars, the distributivity of vectors, under addition, under scalar addition. So here what I'm doing is adding two vectors together and then scaling the result. Here what I'm doing is adding two scalars together and applying them to the vector. The last thing I want to do in this video is take a look at a proof of one of these properties. Your textbook proves properties 1, 2, and 3. I'm going to prove property 7, the associativity of scalar multiplication. I'll start by stating what the claim is, and then I'll walk you through my thought process on how to prove that. The textbook lists this as a given. It's called the associativity of scalar multiplication, and it says that a times the vector u scaled by v is equal to the vector u scaled by the product of a and b. What I've done is just very slightly restate that. Because I'm writing a proof, I need to make sure that my reader understands world I'm working in here. So I've said that for a vector u, I've named the vector that I'm going to work with. It's going to be a generic vector. In fact, I could probably define this even a little bit better. Let's look at that in just a second. I've said what vector I'm going to be working with, and I've indicated where that vector lives. It lives in Rn. Again, n is a number. I just don't know which number it is at this point. It could be R3, it could be R17. My point in using an n is to make it clear that when I'm done, that it doesn't matter what n is, this thing that I'm about to prove will hold true. So for any given vector u, I'm calling it u, any vector in Rn, and two numbers a and b that are real numbers, they are in the set of real numbers, my claim is that a multiplied by u scaled by b is going to be the same as u scaled by the product of a and b. The way I'm going to do this is I'm going to show what happens when I do b multiplied by u, and that what then happens when I multiply a times the resulting vector. I'll do that in one column. And then in another column, I'll multiply a and b, and I'll multiply the result of that by u. In fact, ab, because I don't know what they are, the result will just be ab. But I'll multiply that by each component of u, because that's what scalar multiplication is. And at the end down here, I'll show that the two are equal. Now, this is okay to do as long as you take very careful precautions not to use algebra across the equal sign. What I'm trying to prove here is that these two are equal. If I say divide both sides by a, then I'm using the fact that they're equal to prove that they're equal, and that's not allowed. So I can work with one side until it looks like the other, or I can work with one side and then separately work with the other side and show that no matter what I do to the two sides independently, the result will be the same. And that's the approach that I'm going to take in this proof. Now, I said I should have possibly defined u a little bit more specifically. I didn't, but I can do that now. I'm going to say, let's do this too. Let's write that this is where my proof is starting. Let's let u be the vector. Let's go with u sub 1, u sub 2, all the way down to u sub n. That is an n-dimensional vector, n being some dimension that I don't know. Then u, if that's u, right, then b times u, this should probably be a semicolon. I won't dock you for that, but I was an English minor, so I'm a little bit pedantic about my punctuation. If u is this vector, then b times u, notice that what I'm doing here is this inside multiplication first. B times u is going to be, I think I want to move that because I need the right-hand side of my screen for the right-hand side of the equation. Bu is going to be b times the vector u sub 1, u sub 2, all the way down to u sub n, right? And we know what that is because we've done scalar multiplication for it. That is the vector b times u sub 1, b times u sub 2, and so on, down to b times u sub n. It's that vector. That's a new vector. And I've done that. And a times that resulting vector, b sub u, b times u, is going to equal, I'm going to have to scooch down here a little bit, a times the vector b times u sub 1, b times u sub 2, down to b times u sub n. And again, by scalar multiplication, what this means is multiply each component by a, so I'm going to get a, b, u sub 1, a, b, u sub 2, and so on, down to u sub n. That is the result of multiplying a vector u first by b to get bu, and then by a. That's the result. So what I've said here is let u be defined like this, then what I get when I do this operation is this vector, and what I get when I do this operation is this vector, and I'm going to put kind of an odd period at the end of my sentence there. And I'm going to start in the next column. I'm going to say, now this is a new statement because I'm working on the other side of the equation. I'm going to say, since A and B are in R in the real numbers, AB is also a real number. Therefore, I'll use that funny little symbol again. AB is a scalar. And scaling U by AB is going to give me AB times U1, AB times U2, and so on down to UN. Now it's pretty easy to see here that I've ended that sentence with this result. I ended this previous work with the same result, and I might be tempted just to say, should be obvious, right? I don't need to write anything else. But in the best practice of proofwriting, I'm actually going to draw the conclusion for my reader. I'm going to say, since the results are the same, no matter which order we do them in, A times B, U scaled by B, is the same as U scaled by AB. And that's the end of my proof. You may notice a similar approach in the textbook's proof of property 1. It says for the vectors in Rn, U and V are Rn, in Rn, the sum of the vectors is in Rn. That's one of the properties that we're allowed to work with. Then they spell out what U and V are in component form with a plus sign between them. Then they show the components added together inside a single vector. And the final statement is, since each component, ui plus vi, of the vector u plus v is a real number, the vector u plus v, the vector you get by adding together two vectors, is also in the space Rn. So they've drawn that conclusion for the reader. There's no single right way to write a proof, but there are lots of wrong ways to do it. This class may be, for many of you, the first time you've been asked to prove really anything. And I've tried to show you, kind of as we've gone through these videos, I've tried to show the occasional proof here and there. But at some point, you're going to have to start doing your own proofs. I've done this one for you because I wanted you to see sort of what the process looks like, but I'd really quite like for you to try doing one yourself. So one of the activities I'm going to ask you to do in this particular section is to prove one of these properties.